Hello, welcome. Okay, what the heck is going on here? Let's pop into the real world and find out. Computers are based on a binary system. That means they work in base 2 with only zeros and ones. Zeros represent latches that are off, and ones represent latches that are on. So, to understand addition of binary, first we have to really understand what binary represents. So, in binary, the furthest digit to the right is the ones column. So this 1 represents 1 in base 10, which is our number system. So this 1 is just 1. So if we're looking for what this string of numbers equals, we can just add together the place values that the ones represent and ignore the ones the zeros do. So if this is 1, we just add 1 to our addition table. Then each space you go over to the left in binary is double the space previous to it. So the next column would be the 2's column. We have 1, 2. Let's add a 2. Then again, we double. This is the 4's column. So we have a 4. Then this is the 8's, the 16's, and the 32's. We don't have any of those, so we won't add them to our addition table. But we do have a bit in the 64th place. So we will add a 64 to our addition table. We add these up, and we'll get 1, carry the 1, we get 71. So 1000111 equals 71. Understanding that each bit to the left is twice as much as the bit to the right is pretty easy. It's just like in our number system, where each bit to the left represents 10 times as much as the first bit. So say a number like 11. This column, we have a 1. That just represents 1. But in this column, we also have a 1. But in our base 10 system, that 1 represents a 10, meaning that this column is 10 times more than the column to the right. And if we were to add 100 to this, we also have a 1, but this represents 10 times more than 10, as 100 is 10 times more than 10. We are going to use this to now understand binary addition. So we have two examples here. We have 55 plus 55, and this is not 11 plus 11. This is binary, so 1, 1 plus 1, 1. So first we'll solve 55 plus 55. So as you know, 5 plus 5 is 10, right? And we represent that by drawing a 0 down here because 10 has 0 in the ones place. But we carry a 1 representing that 10 has 1 in the tens place. So then we add 5 and 5, get another 10. But then we also have a 1 up here, so we still have 1 in the ones place. 1 carries down. Since we got 10 from these two 50s, we'll carry the 100 to the next column. The 10 times more than that column, as we just said. So then we carry that down. We end up with 110. Okay, so now we can move on to binary. This should be just the same, except we treat each column as twice as much instead of 10 times as much. So 1 plus 1, 2, right? No, because we don't have a 2 in the binary system. We represent 2 as carrying a 1 over to the next column, because 2 is twice as much as 1. So we can just represent it as 1 in the column that's twice as much as the first column. So we have a 0 down here, and we carry a 1 to the next column. In this column, it might look like we have 3, but no. We just have 3 1s or 3 2s. So we can add a 1 and a 1 just like in the first column. We'll have to carry a 1 to the next column, but we also have the 1 left over, just like here. We carry that down. Then we just carry the final 1 down, and we don't end up with 110. We end up with 1, 1, 1. This is actually 6. There's 0 1s, so no 1s, and we have 1, 2, and then this is the 4s column, and we have 1, 4. So 2 plus 4 equals 6. You'll also see that if you break down our 2 original binary numbers into what they actually represent. 1 in the 1s column and 1 in the 2s column. So basically we have just 3 and 3. And obviously those add together to make 6, our answer. How is it computers do these things, you ask? Well, this is how. This is what's called a full adder. These are the inputs, A, B, and C. 2 inputs are for the first numbers, and C is for the carry input. Just an interjection here. The carry input is used to input the carry output from the previous full adder. So if you have like 8 of these lined up in a row, like we're going to have later, they're all feeding their carry output into the next one's carry input, and that is how we can add numbers greater than 1 bit by just chaining these full adders together. These lines are all the wires, and then these boxes are the logic gates. Then we have our outputs, the sum and the carry. Let's say we're trying to add 1 plus 1. Let's put those in the A and the B input, right? Let's keep track of it over here. 1 plus 1. 1 from A will travel through this wire and also down this wire. And then 1 from B travel through this wire and also down to this wire. So we have come to the first logic gates. Logic gates are how computers perform logic on numbers. All you need to know for now is that XOR gates only output if one of the 2 inputs is on. AND gates only output if both the inputs are on, and OR gates output if one or both the inputs are on. So we see at our first XOR gate, we have a 1 as this wire is on, and a 1. So this will not output a signal because XOR gates, like I said, only output if only one of the wires is on. So let's go to our next gate, the AND gate. Since the AND gate is getting 2 on signals, it will release a 1 or a signal. This goes into the next gate, an OR gate. And remember, OR gates, they pass signal if one or both are on. 1 is on. So that passes the signal out. And we have a carry signal. So just like we would see with this, we would put a 0. This is the sum. That's the sum output. So there's no output from this wire. But there is an output on the carry wire. So we would need to carry a 1, just like we did in the last video. So this one, we end up with 1, 0. Great. Let's try a different number now. For this next example, we're just going to try a 1 and a 0. So through the A input, we'll have a on signal, and then 0 on B, so we don't have any signal running through there. Let's go to the first gate again. XOR. Again, we have 1 and not both signals on, so this will export a signal this time. But at this bottom AND gate, we only have one and not both of the signals, so we'll push a 0 out, or no signal. Now this next XOR gate sees one of its inputs on, one of its inputs off. So 1, not both. Great, so it outputs a 1. And our sum is 1. This AND gate has a 1 signal and a 0 signal. So it only sees 1, and since both of the inputs are not on, it will not output a signal. So we end up with 0 over at the carry and 1 over at the sum. Let's try that with our addition table. So we have 1 plus 0. Great, we can still represent that in the ones place. So it's just 1. Sum of 1. And that is exactly what you see here in orange. So down there at the bottom, you can see the 3 inputs, A, B, and the carry input. You can see in blue are the 2 XOR gates. Green are the AND gates, and purple is the OR gate, and those are the 2 outputs at the end. So with this setup, we can do exactly what I just showed you. That's A and that's B. We can do 1 plus 1, and we'll get a carry output, just like I showed before. We can also do 1 plus 0, and we should get a sum output. There we go right there. With this, it's much easier to just flick a bunch of levers and see what happens. So you see with 1 plus 1 plus 1, we'll get a sum output, so an output on the bottom of the column, as well as a carry 1 that we'd have to bring over to the column to the left. After a little while, I condensed that down to this little circuit, which for a 1 should just get sum. Great. 2 will get a carry. And for 3, we'll have both sum and carry on. And that is what I put into this big mess right here. From up here, you can see the 1, 2, 3, 4, 5, 6, 7, 8 orange little chips in the system. Each of those are a full adder and can add 2 bits together, including a carry bit. And they're all wired up to add up 8-bit numbers. This is the input panel, where the dark blue represents inputs A, and red represents the B inputs. So we can do something like 10 plus 10, let's say. Then these lighter blue lamps indicate what the output is. So we see we have one on for the 4's place, and we have one on for the 16th place. So together, these make 20, which is what we would expect from 10 plus 10. And that's really all it is. That machine is just plonked right here and plugged into these light blue wires and these green wires to communicate with the rest of the system. In all honesty, like, this is the only part that does computing. The rest of the stuff, this is all just to decode your inputs and encode the outputs back into the display, because it's not that fun to input numbers in binary when we're so used to our base 10 system. But thanks to all of this infrastructure, we can input on the keypad and then get outputs that show us in numbers that we recognize. Let's do a demonstration right here. Let's add 126 plus 46. Great, we get our output. We have 126 plus 46 equals 172. This, once you break it down like we just did, it's pretty simple. We just take the inputs and we decode them into binary, and then we can just use our column adding with the binary numbers in the little 8-bit circuit I showed you over there. And then we just decode that back into base 10 and display it like this. There's no magic to it. It's just simple adding ones and zeros together. Now, am I just going to ignore the fact that this tiny little thing is more powerful than my giant 8-bit adder because I built that before I knew that there were other people who did this kind of stuff in Minecraft? Yes. Yes, we are. Thank you for watching.